One of the most important and basic things that you're going to be asked to do in AP chemistry is find the formula weight or atomic mass, or excuse me, not atomic mass, molecular mass of a substance. And if you look, we have an example of carbon dioxide, and really all you need to be able to do is look at the substituent pieces and go ahead and add the masses of those. So because I have one carbon, and there's the atomic mass of carbon. I have two oxygens, so I have two oxygens, and that's the atomic mass of oxygen. So the question always comes about, do I need to take it to this level of precision whenever I'm reporting the molecular mass or the atomic formula? And the answer is generally not. Usually when you look at the AP formula chart, instead of reporting it to this many digits, they usually instead report them to about two decimal places is usually what you see. But the answer is you should always use the greatest degree of accuracy that you have in the formula chart or the periodic table that's given to you. So if they do give you 12.0000, then you should use 12.0000. So you always use the highest degree of specificity that you can. You can use this idea of the gram formula mass, and you can actually calculate what's called the percent composition. And that's just an easy way of trying to express the role that each atom is playing in the molecular mass of the whole. Okay, so it's a really good idea of trying to say this is the whole, and this is the mass contributed by hydrogen. This is the mass contributed by carbon, and so on. And actually, this is the percent composition of the atmosphere that you see. You see the atmosphere is actually 78% nitrogen by mass, which makes up the vast majority of the atmosphere. Oxygen is 21%, and then everything else that you hear about in terms of the atmosphere represents less than parts of 1%. So you have things like water vapor and carbon dioxide, and all those things represent a very, very, very small percentage by mass in the atmosphere. In this example, it says you have a particular strain of hemoglobin turns clear whenever iron is removed from a protein. Hemoglobin has the formula 738, 1166, 812, and then 203 oxygens, and then two sulfurs and an ion. It says determine the molecular weight, that's another way of saying it, molecular mass or something along those lines, of the strain that lacks iron. Okay, so the fact that it lacks iron means I'm going to cross it out. Now generally what you would do here is you look and you say, okay, I've got 738 carbons. So you'd write 738 and you would multiply it by 12, and then you would use the specificity of the periodic table that's given to you, minus 12.01, so then I would use that. Then you have 1,166 hydrogens. The hydrogen specificity that I have is 1.008, and then I have 812 nitrogens, which is 14.01, and then I have 203 oxygens, and my periodic table says 16.00, and then finally you have two sulfurs at 32.06 even. Okay, so at this point you would take all these and you'd multiply them out. I'm going to trust you to do that on your calculator, and whenever you do this, the total you end up getting is 27,726.948. But whenever you look at these in terms of significant figures, you can't report it as that right there. So instead, you actually have to round this last digit to where it's a 9.5. And what that represents is that's the number of grams per mole of hemoglobin. Now, hemoglobin is a very large molecule. It would actually be slightly heavier if you actually added the iron as well. In this next one, it says the chemical formula for thiamine, I should say for thiamine, one of the four major nucleotides of DNA is this. You have C12H17Cl N4OS. It says determine the percent composition of carbon. Well, now in order to figure out the percent composition of carbon, you really need to take the part of carbon, and then you need to divide it by the whole and multiply it by 100. That's how you find the percent of anything. Part divided by the whole times 100. So that makes finding the whole the biggest key part of this particular question. So you do the same thing that you did in the previous example. You have 12, carbons is 12.01, you have 17 hydrogens at 1.008, you have 4 nitrogens at 14.01, you have 1 oxygen at 16.00, you have 1 chlorine at 35.45, and then you have 1 sulfur at 32.06. At this point, we would multiply all these values out. The only one that I'm going to report is the one that I'm really interested in this case, which would be 12 times 12.01, which is, it's going to be pretty close to 144, but let's go ahead and put it in the calculator just to make sure. 12.01, so you get 144.12. Okay, once you do that, you have to multiply all the rest of these values out. And so carbon at 144.12 is going to go right here on the top. And then the total value that you get right here, just like we did in the previous example, is going to go on the bottom. And I'm going to leave it to you to go ahead and figure out what the percent composition is. But that's the procedure that you would use.